direction and automation and mathematics stronger, almost like a programming language. Okay, so show me info. All those things align and then to realize how they do it. In case of value recommend. Okay, in college of good practice. All full-time PhD scholars. All the class. We associate with that scholar.
ఎంతటి ఆవిడి
മലയാള മനോരമയിൽ വന്നൊരു വാർത്ത കുറച്ചു നേരം മനോഹരമായിട്ട് മീൻകറികളുമായിട്ടും മക്കളുമായിട്ടും ഒക്കെ എന്തെങ്കിലും ചെറിയ വഴക്കുകളോ അറിയാതെ പോലും ചില വാക്കുകൾ അസ്ത്രങ്ങൾ പോലെ ആ വാക്ക് അസ്ത്രത്തിനെക്കാട്ടിൽ വലിയ മുറിവുണ്ടാക്കുന്ന പോയതല്ലേ പിന്നീട് ചോദിക്കാനോ ഒരു സോറി പറയാനോ ഒന്നും തയ്യാറാവാറില്ല.
Yes sir, tell me sir, how are you now?
Sir fine sir. అప్పుడే వచ్చేసావా?
టెస్ట్ చేస్తున్నాను అంతే, మళ్ళీ అప్పుడప్పుడు మళ్ళీ చేసుకోవడానికి టెస్ట్ చేస్తున్నాను.
శివాడు సార్ మీద సౌండ్ వస్తున్నట్టు ఉంది చూడండి. సౌండ్
ఏంటి ఆదివారాలు శనివారాలు ఏం లేకుండా మొత్తం అంతా ఒకటేలాగా కరోనా.
సర్కారీ నౌకరీ కాదురా, సర్కారీ నౌకరీ కాదు.
మాకే లేవు, మాకు కూడా లేవు సండేలు. మా అకాడమిక్ క్యాలెండర్ లో కూడా సాటర్డే ఇప్పుడు వర్కింగ్, ఇప్పుడు 2 సెమిస్టర్లు అయింది.
అందుకోసం ఇలా కరోనాలో జనాలు చచ్చిపోతున్నారు.
అమ్ములకు కాదు, మేము చచ్చిపోతున్నాం జనాల కంటే ముందు. సో ఎప్పుడు స్టార్ట్ అవుతుంది మరి లెక్చర్
నీది? నేను జస్ట్ ఒక అర్ధగంట ల్యాబ్ విజిట్ పెడతాను, అదే పొంగల్ స్టార్ట్ చేసే.
గంట సరిపోతుందా, గంటన్నర కొట్టాలా?
గంటన్నర కొట్టు, గంటన్నర 2 గంటలు నీ ఇష్టం.
సేపు కొట్టమంటే సేపు స్లైడ్ లో ఒకటే ఎక్స్ప్లెనేషన్ పెంచుతాం అంతే.
నీ ఇష్టం, 1 దాకా తీసుకో, 1:30 1 దాకా తీసుకో.
2 గంటలు కొట్టమంటే 2 గంటలు కొడతాం.
సార్ స్టార్ట్ చేయండి. స్టార్ట్ చేయండి. ఇంకా
స్టార్ట్ చేయమంటావా? పార్టిసిపెంట్స్ ఇంకా 12 మంది. ఒకసారి వాట్సాప్ లో పెట్టావా మెసేజ్? ఒక 5 నిమిషాలు.
సరే సరే.
సిద్ధారెడ్డి సార్,
సార్
మీ పక్కన మీ అమ్మాయి వచ్చి పోతున్నాయి, ఉన్నారా లేరా?
మా అమ్మాయి, మా బాబు ఉన్నాడు.
గుడ్ మార్నింగ్.
చెప్పినా ఈరోజు సార్ బ్యాటరీస్ గురించి చెప్తాడు, వినండి అని చెప్పిన.
బ్యాటరీ ఫ్యూయల్ సెల్ రెండు
బ్యాటరీస్ ఫ్యూయల్ సెల్ గురించి చెప్తాడు అని చెప్పిన.
కొంచెం ఇంట్రడక్షన్ లాగంటే సార్, మనం రీసెర్చ్ లోకి డీటెయిల్స్ లోకి వెళ్ళట్లేదు, జస్ట్ ఇంట్రడక్షన్. అది ఎలా మనకి రెన్యూబుల్ ఎనర్జీతో కనెక్ట్ అయి ఉంటే దాంతోనే. ఇంకా బ్యాక్గ్రౌండ్ బాగా పెట్టినారు సార్ మీరు.
మా వాళ్ళే సార్ అంతా, ఈ కాలం అంతా డిజిటల్
ఏమంటాము డిజిటల్ స్టూడెంట్స్ ఇప్పుడు.
యూట్యూబ్ లో కూడా లైవ్ వెళ్తుందా?
వెళ్తుంది సార్.
రికార్డింగ్ కూడా ఉంది.
రికార్డింగ్ కూడా
ఎవిడెన్స్ చూపించుకోవచ్చు నువ్వు.
మెయిలే పంపలేదు నువ్వు సార్.
మెయిల్ వచ్చింది కదా, మెయిల్ పంపబోతుంది.
మెయిల్ గ్రూప్ లో పంపించినాము సార్ అందరికి ఒకటేసారి.
మళ్ళీ స్పెషల్ గా పంపించాడు కదా.
అది నా మెయిల్ ఐడి ఏదో మిస్ అయినట్టుంది, నేను గ్రూప్ లో చెక్ చేసిన.
నిన్న సాయంత్రం మళ్ళీ వచ్చింది కదా.
ఇక్కడ రాలే
నిన్న సాయంత్రం కూడా రాలేదా?
2 మెయిల్స్ ఉన్నాయి కదా, రెండింటికి పంపించాము. ఎన్ఐటి వరంగల్ ఒకదానికి, NIT W, తర్వాత ఇంకోటి మీ పర్సనల్ మెయిల్ కూడా పంపించాము. శివారెడ్డి ముందర పంపించాము.
వచ్చింది, ఇన్విటేషన్ వచ్చింది. పొద్దున్న పంపించింది 18 hours ago and 1 hour ago. Call now, join at 9:30.
వచ్చింది కదా.
వచ్చింది.
ముందు కూడా 12వ తేదీ నైట్ పంపించాము.
ఓకే,
డిసెంబర్ 12.
ఎందుకంటే అది FDP అన్నది రెన్యూబుల్ ఎనర్జీ కదా సార్.
అవును సార్.
బట్ ఇక్కడ ఏమొచ్చిందంటే మిషన్ లెర్నింగ్ మోడల్స్ ఫర్ డిసీజ్ డయాగ్నోసిస్ అని వచ్చింది. అందుకని
అది వేరే వాళ్ళది ఉంటుంది. అది వేరే వాళ్ళది ఉన్నది. దానికి మనకి ఈరోజు 18 hours ago వచ్చింది లెర్నింగ్. ఇది అనేది సిఎస్సి లేదు సార్ ఈరోజు. సార్ లేదు సార్, ఇంకొకసారి ఫార్వర్డ్ చేయండి. మురళి పంలోకి చెక్ చేస్తాను.
నేను పంపిస్తాలే, ఉండు.
సార్ ఉంది సార్, ఇది వెళ్ళిపోయినాయి. సమ్ ఫోల్డర్ లోకి వెళ్ళిపోయినాయి.
పంపించాను చూడు, ఇప్పుడు నా దగ్గర నుంచి కూడా వచ్చి ఉంటుంది చూడు.
డిసెంబర్ 12వ తేదీ పంపించాము చూడు సార్, 8:56 PM.
అదే అవి స్పమ్ లోకి వెళ్ళిపోయినాయి సార్, ఇన్బాక్స్ లోకి రాలేదు. ఇప్పుడు చూసాను, అవి అన్స్పమ్ చేశాను.
మొత్తం స్పీకర్స్ అందరికి డిసెంబర్ 12 నైట్ పంపించాము.
ఓకే, రెండింటికే వెళ్ళాయి. ఎస్ఎంఓ అని 2 బాక్సులకి స్పమ్ లోకి వెళ్ళిపోయినాయి.
అదే మాకు ఇంతవరకు కంప్లైంట్ అయితే రాలే, ఫస్ట్ మీ నుంచే.
అదే నేను చూడలేదు స్పమ్ నుంచి.
నాకు కరోనా వచ్చేమన్నా మైండ్ దొబ్బిందా ఏమని నాకు డౌట్ వచ్చా. ఈ మధ్య కొద్దిగా రిమంబరింగ్ తగ్గింది.
చాలా బెటర్, తిరిగే ఒక్కర్లా.
అంతే అంట.
నీ దగ్గర అప్పులు తీసుకున్న వాళ్ళకి కూడా బెటర్, నీకు ఇచ్చేవాళ్ళు నువ్వు మర్చిపోతావు.
అదే అట్లా ఏమన్నా మర్చిపోయినా ఏమని మళ్ళా నిన్న ఛాన్స్ వాళ్ళు ఇచ్చిన, ఇంటికి వచ్చిన తర్వాత మళ్ళీ చెక్ చేస్తే పంపించింది అంటూనే ఉంది.
ఓకే, మనము రేర్ గా స్పమ్ ఫోల్డర్ చెక్ చేస్తాం. చెక్ చేయం కదా, ఇన్బాక్స్ ఒక్కటే మనకి విజిబిలిటీ ఉంటుంది. ఏం సార్, ఫుల్ గా రికవర్ అయినట్టేనా? ఇంకేమైనా చిన్న సిమ్టమ్స్ ఏమైనా ఉన్నాయా?
ఉన్నాయి సార్, కొద్దిగా అదే లంగ్స్ కొద్దిగా ఇంకా పూర్తిగా రికవరీ కాలే. ఇంకా కొద్దిగా ఆయాసం వస్తుంది స్టెప్స్ ఎక్కినా.
అది అంతకు ముందైనా వచ్చేదిలే నీకు, నువ్వేదో ఇప్పుడు కొత్తగా చెప్తున్నావు, ఇంతకు ముందు రాలేదు నీకు ఆయాసం.
అంటే ఇప్పుడు నడుస్తున్నా గానీ వస్తుంది కదా ఇప్పుడు.
అది నీకు ఇప్పుడు విజువలైజ్ అయింది అంతే, అంతకు ముందు కూడా ఉంది నీకు ఆయాసం. సరే అయితే స్టార్ట్ చేద్దామా?
16 మంది ఉన్నారు. జాయిన్ అవుతారులే.
ఇండస్ట్రియల్ విజిట్ ఏదో అన్నారుగా.
అదే ఇప్పుడే అది చేసిన తర్వాత నీకు చెప్తాము, నువ్వు స్టార్ట్ చేద్దావు.
ఓకే. వర్చువల్ గా ఇండస్ట్రీకి తీసుకెళ్తావా?
ఇండస్ట్రీగా సోలార్ డ్రైయర్ ప్లాంట్. ఇండస్ట్రియల్ విజిట్ అని రాసాం, రాయలేదే. సోలార్ డ్రైయర్ కదా, క్లారిటీగా రాసామా? మొన్న ఇండస్ట్రియల్ విజిట్ అయిపోయింది, నువ్వు చూడలేదు. సోయా ప్లాంట్.
సోయా ప్లాంట్ చేసావా? పన్నీర్ చేసావా?
సీడ్ నుంచి పన్నీర్ వరకు మొత్తం విజువలైజ్ చేసేసి.
ఇప్పుడు వర్చువల్ గా చూపించావు దాన్ని కూడా?
దాన్ని కూడా వర్చువలే, కేకులు చూపించు.
ఓకే
సరే సార్, అయితే స్టార్ట్ చేయండి మాస్టరు.
ఓకే. So dear participants, good morning to all of you, and I welcome the today's speakers, Professor V. Sivareddy sir and Dr. S. Murali Mohan sir. I welcome you for the today's faculty development program on renewable energy intervention in industry and domestic and commercial applications. So today is the second week morning session. That is first part is virtual visit of solar dehydration plant established at Incubation Center, RGM set Nandyala. So this will be explained by Professor V. Sivareddy sir. So over to you, sir.
Okay, sir. Thank you, sir. I think in this week I am coming fourth time. So last sustainable development by the renewable energy intervention we discussed, and that one of the project successfully implemented project. That project virtual visit today we planned. I think last Friday we did the virtual visit of our soya milk plant. I think you people are enjoyed from seed to the cake. We visualized it. Next, this also will get same experience. Solar hot fluid generator based dryer for agro industrial application purpose. I already explained, but just brush upping before virtual visit. What is the purpose of drying? Means we are removing the moisture for long-term storage. Long-term storage, two types of the methods we are using. One is cold storage. Second one, removal of the moisture to reduce the enzyme activity, enzyme and bacterial activity. We can't kill the enzyme and bacterial activity, but we can reduce that activity by two methods: removal of the moisture. Second one, storage, cold storage. But I already mentioned in the cold storage, major problem you can see freezing. The cold storage, normal loss of nutrients 40 to 60% is takes place. We are feeling we kept in a cold storage means nutrient levels we are maintaining. We are not maintaining the nutrient levels. Loss is taking place. Second, I already mentioned thermal shock. Due to the huge temperature difference, the cold storage temperature 4 to 5 degrees, ambient temperature is 50 degrees. Sudden thermal shock is came to the picture. Damage 30% of the product damage due to the thermal shock is takes place. So to eliminate that one, the best method, removal of the moisture. Removal of moisture generally industrial drying. Already we are doing industrial drying by PNG or pipeline natural gas based burner or electrical heater based dryers we are using in industry. Example also we discussed one example. Again I am recalling that example is Priya pickles. In I think in Andhra famous. And not only Andhra, in USA also we are exporting the Priya pickles. The cost in all seasons cost is same. 100 grams Priya pickle will come 50 rupees. In all seasons, how it is possible means whenever harvesting is taking place, that time they are purchasing tons of the tomatoes or whatever pickle minimum needs. At the time of harvest, lowest cost, they will get 10 rupees, 5 rupees, 2 rupees. Then they are doing industrial drying and they are storing. Why? Because they can't kept in cold storage. Means again energy loss is taking place, and I already mentioned nutrient loss. For export, nutrient loss they will not allow. So that is also one of the drawback. That's why they are doing industrial drying. And next, our target is solar drying. Compared to industrial drying, solar drying main advantage, the temperature is not crossing 60 to 70 degrees. If the temperature is not crossing 60 to 70 degrees means the sugars, melting of sugars will not take place. If melting of sugars in the agriculture produce is taking place, then color change will come into the picture and the nutrient loss also will initiate. That one we can control by solar dryer. Simple logic of the principle in dryer means we want to remove the moisture, surface moisture and bonded moisture. Surface moisture easily by flow of air, low relative humidity air, we can remove. And bonded moisture, we have to create the capillary action to bring the moisture from the body to surface. Then only we can remove the moisture. For that only the drying techniques are required. You can see simple, we are increasing the temperature means automatically relative humidity is decreasing. So more moisture absorption capacity we are increasing. In solar drying in olden days, I think last 2000 years maybe, we can see we are doing open sun drying only. We are doing like chilies, we are drying in open sun only. Dal, paddy, everything we are doing open sun drying only. But the drawback of open sun drying, uncertainty of the solar radiation is there, and it is taking more time. Any perishable goods, we can't do the open sun drying. If you are doing means the color change is coming to the picture, the quality of the product is reducing. For that only automatic drying is required. You can see these are the solar radiations. Okay. For this, we developed, we proposed and developed one solar dryer. Here, three things we did. We separated solar thermal unit separately. That is also we used ETC with heat pipe. So we separately industrial solar heating system we used total. So in this by ETC with heat pipe, we are heating the thermal oil, means heat transfer fluid. The storage capacity we maintained 500 liter storage capacity. So this is one cycle. It is not linked with the dryer. Even though dryer is not working in early morning onwards, we can store the solar energy. Next, whatever the energy we are storing, that energy according to need of the dryer. Initial conditions, we required high airflow rate and low moisture air. At that time, mass flow rate of the air we can increase by increasing the blower speed. Automatically the surface moisture immediately we can remove in the dryer cabin. You can see dryer cabin also conveyor belt dryer cabin we selected, not box type or cabin type dryer cabins, but because full-fledged industrial model. I will visualize that one later. Once surface moisture is removed, at that time just heating of the product is required. Then we are doing the heating of the product due to the capillary action, bonded moisture ready to come to the surface. It will take time. At that time, we can reuse the air. Easily we can reuse the air. At that time, again solar system separately it will work, and whatever the air already heated, same air we are recircling inside the dryer cabin. We can measure the relative humidity of the air. If relative humidity of the air is increasing more than 60, then we are substituting some fresh air, again recycling that air. At least 1 or 2 hours we can do that one. Then entire bonded moisture will come to the surface. Then automatically we can remove that bonded moisture. Full-fledged drying will complete. I think this is the schematic view of the plant. Now we will see virtual visit of our solar plant, solar dryer plant. This is our terrace area where we installed this solar array. Yes. Yeah, first ETC with heat pipe I mentioned. This is the heat pipe. We are immersing inside the ETC tube collector. You can see that. This is the evaporator part that our assistant will show. This is the entire length, 1.8 meter length is evaporator point. This is the condenser unit. The top side is the condenser unit. This total we are immersing inside the tube, and only condenser we are inserting the manifold. This is the tube. You can see in this tube coatings is there. 2 glass tubes evacuated for increasing the absorbability, increasing the emissivity, decreasing the reflectivity. We are doing the copper, iron, nickel coatings on the glass tube. Dark black shade is coming inside. Copper coating is there. That's why brown color is visualized. In between the tube, we are immersing the heat pipe. That heat pipe condenser is inserted into the manifold. Now I will show the manifold. This is the structure. You see SS304 structure we used, lightweight and rust free structure, and grouting we did with the foundation. Otherwise, due to the heavy winds, the line disturbance will come into the picture, then joints will break, leakage of the system is came to the picture. This entire structure. Per row, 5 collectors are connected. You can see. Per row, we placed 5 ETC tube collectors are placed. This is the 5 collector, 1, 2, 3, 4, 5. Each collector contains 20 tubes. One tube length 70 mm diameter, not 70 mm. Inside diameter 58 mm inside diameter, and length is 1.8 meter length. And you can see whatever the condenser, this heat pipe is there already immersed in ETC tube. That heat pipe is inserted in the manifold. This is the manifold. Each collector contains one manifold. This is the connection. You can see. This is each manifold is connected. Flange joints we are used with neoprene rubber insulator. Flange joints we did. This is the inlet. From the storage tank, we are getting the inlet. One more solar wastewater evaporator I explained in a sustainability development lecture. That one. And this is the first row. 2 rows we maintained. Each row contains 5 collectors.
Sir, are you playing video?
Yes, sir.
Video is not visible, sir.
For you or all?
I think for all.
No, sir, it is visualized.
But it is not shared video.
Sir, it is clearly visible.
Visible, sir.
Actually, I am also unable to see the video.
Why? The speakers are getting a problem. 1 minute. Now?
No. I think participants are getting or not.
Yes, sir. It is on live. Share mode only. Any participant respond, the video is visualized or not?
Sir, it is clearly visible and audible, sir.
Okay, thank you. Thank you.
Video.
Video also.
It's visible and audible.
Sir, again you log in.
No
Sir.
no videos there. Only that conveyor belt based dryer cabin, that paper only.
I also put
No videos there.
schematic diagram of solar.
That schematic diagram only.
Only
Yeah,
schematic diagram is showing. Again, I will share. 1 minute.
You share the video, sir.
Now?
Yeah, now it is okay.
Yes, yes.
Okay. So this is the ETC. The two collectors were connected by the flange joint with neoprene rubber insulator. This is the tube. We are immersed in the glass tube. I think from starting again I will show what is heat pipe later. Otherwise, now this is the heat pipe. Heat pipe top portion is condenser. Total 1.8 meter length is the evaporator. You can see. He will show. This is yes. This is the heat pipe. Each ETC tube we immersed this heat pipe. This condenser portion is in manifold remaining in the ETC tube. I will show the ETC tubes now. This is the tube inner view. You can see two glass tubes we evacuated for increasing the absorbability. Why? Because there is no metal. Increasing the absorbability, emissivity, and reducing the reflectivity. Nickel, chromium, and copper. Sometimes SS also they are doing. Three types of the coatings they are using. In between, we are immersing with the support of aluminum foil structure. We are immersing, centering, in center we are immersing the heat pipe. Main advantage of heat pipe is to enhance the heat transfer at lower temperature difference also. That's why with the ETC tube itself, we are achieving more than 100 degrees temperature. Mediator is not liquid because mediator not a water. Water 100 means it will generate steam. Terminal oil we are using. Now you see the structure. SS structure we are using. 304 metal SS 304s we are using. Here also ground grouting we did for stability of the structure. In the foundation bolts, you can see the foundation bolts for effective structural support. For this is the manifold outlet. Now you see this is the view of the ETC with heat pipe collectors. These are the 5 collectors. Each collector contains 20 tubes. Each tube length is 1.8 meter. Total area of the collector is 3.2 meters square. Like this, 5 collectors are connecting. In the manifold, the heat pipe condenser part is there. Through the manifold only, heat transfer fluid is transferring. This each collector we are joined by the flange joints. Everywhere we are using neoprene rubber. Why? Because neoprene rubber temperature resistance is more than 150 degrees. So best sealing effect we can achieve. This is the inlet of the collector. From the tank, we are getting the inlet, storage tank. I will show. This is one more view, one more development of solar wastewater evaporator. This is remain 5 collectors. So total 10 collectors. Each collector area is 3.2 meters square. So total 32 meters square area of solar collector is installed for drying of 200 kgs loading capacity dryer. Maximum capacity is 200 kgs. So only through the manifold only heat transfer fluid is transferring, nothing else. Remaining area only heat pipes are there. If due to the monkeys or any wind loads, if any collector is failed, there is no leakage, only temperature drop will take place. So this is the inlet pipe. So you can see, visualize this deep visualization of the flange joint. You can see here we are immersing ETC tube. This is the entire insulated manifold. Glass wool insulation we are using because high temperature is there. You see shading effect is coming. So this is the inlet pipe. 2 collector single T-joint inlet we are given. This is the outlet of 2 collectors. From the inlet, this is from the inlet. Yes. So this is the outlet, one controlled valve we mentioned. If solar radiation is coming, we want to direct utilize the thing, then we will open this valve. We will open this valve. Gate valves, all valves are gate valves only. If I open this valve, means directly it will go to the solar dryer unit. Solar dryer unit is available downstairs. If I closed this valve, if solar radiation is not available, then I will close the inlet valve of the collectors. Two collector inlet valves are there, I will close. Then whatever the hot fluid is available in tank, directly it will go to the solar dryer cabin. So solar radiation is not available at that time also, my system will run. This is the direct, it will enter into the solar dryer unit. Otherwise, if downstairs is requirement of heat is not available, then I will open this wall. I will close the solar dryer inlet wall. I will open this wall. Automatically, it will come to the storage tank. So three way of the connection by the gate walls we arranged. So this is the inlet of the. Our second inlet is there. This is the flow rate measuring instrument. This is the outlet. One flow meter is there. If any problem is there for flow, I want to replace the flow meter, means two walls I connected. I will close the two walls and I will replace the flow meter. Any damage is taking place. This is the storage tank area. You can see. And these two pumps, circulating pumps are connected. One is standby, because if one pump is failed, our system has to run. That's why we kept two circulating pumps. Common inlet and two pumps separate inlet is there. Which pump I want to use, I will open that inlet valve. Other inlet valve I will close. These are the, you can see here two inlets are there. One outlet. You can see two inlets are there. One inlet directly from the collector is coming, one inlet. Another inlet from the dryer cabin, if recirculated heat transfer fluid is coming. So in a storage tank contains two inlet and one outlet. So with one circulating pump, we are capable to do all three operations. This is the inlet of the, from the dryer cabin. Whatever the inlet is coming. Inlet we kept in top, outlet we kept in down. This is a common criteria. There is no special principle. Then this is the control board for running of the blower and temperature measurement and circulating pumps. And blower also, variable type drive blower we connected, so we can increase the blower speeds. Now blower is running, so suction you can see. This is the outlet of the blower. From the blower, air is circulating inside the dryer cabin. Again from the dryer cabin, same air we will get the same air, or by using damper arrangement, fresh air also we can get. I will show the dampers arrangement. Yes, this is the outlet of the blower. This is the inlet of the blower. Two things. So from this blower outlet, this duct directly is entering into the dryer cabin. Dryer cabin I will visualize. It is in first floor. From the dryer cabin, it will go to the dryer cabin. Yes. Yes. You see, from the dryer cabin, we are getting the outlet. This is the dryer cabin outlet. If relative humidity is high, if the relative humidity is high, then direct, yes, you can see. If the relative humidity is high, means I will open this damper, automatically the exhaust, the air will go to the ambient condition. If the relative humidity is low, less than 60%, then I will close this damper and I will open the intermediate damper. Same air I can recirculate. This is the inlet. I will close this inlet damper. If I want to substitute some fresh air, partially I will open this inlet damper. So some fresh air also will enter into the dryer cabin. Already used air also we can recirculate. Means effective utilization of heat energy. So due to the damper opening and closing condition, I can use three-way systems. If relativity is low, recycling of the air I will use, or I want to substitute some fresh air, partial opening of the inlet damper I will use, or initial condition relativity of the air is high, so total air I will leave to the ambient, and every time I will take the fresh charge. So for circulating of the fluids, three methods we used. For circulating of the air also we used. Because of this separation only, we are storing more energy. The efficiency of the system is enhanced, and drying time of the solar dryer non-solar hours is also increased. Now coming to the dryer cabin section, this is the inlet duct. This is the inlet duct. It is connected. Hot fluid, it is entering into the dryer cabin. In the dryer cabin downside, we connected radiators. I will show you. Three radiators we connected. So inlet duct is there. Three inlets we arranged. Why? Because three radiators we are using. I will show the radiators. You can see these are the, yes, three radiators. In the radiators, hot fluid is we are circulating, and through the fins, air is flowing through the fins by it will gain the heat. For visualizing how the dryer cabin drying is taking place, for that one glass window also we arranged. Now this side you can see this is the inlet duct from top, first floor, top floor it coming. So each dryer cabin, this is the outlet duct. Outlet duct again it is going to the blower inlet. From here we are doing the loading. 3-layer conveyor belt dryer. This one 3-layer conveyor belt dryer. Recently we did onion drying. Our employees not cleaned properly. The leftover onion is melted. You can see the leftover onion, whatever is there. Continuation operation of the system is melted. For measurement of the temperatures and flow rates, the sensor connection is there. The instrumentation I will explain later. Today only I am explaining dryer unit. This is my lab. The outlet of the hot fluid, again it is entering into the top side. One is inlet, one is outlet. You can see inside my lab directly I placed this one. everything we connected. Because special areas we will not get in education institute. That is the main problem. Area is most precious thing for education institute. So whatever available in my lab, I utilized maximum percentage of utilization I did. This is the outlet. Top side we are doing the inlet. Conveyor belt 3 layers is there. Finally third layer will get the outlet. The movement of the belt is taking place. You can visualize this one. The movement of the conveyor belt. So just one worker is more than sufficient. I am maintaining only one supporting staff. With that only one supporting staff, I am running solar soya plant and solar dryer also. Both I will not run at a time. I will run one plant. So less manpower. This is the conveyor belt motor. And for washing of the agriculture produce before drying, this is the washing area. Separate washing area also be placed. Now my supporting staff suggested you can visualize it from top view also. Once again, the movement you can see, movement of the conveyor belt is taking place. White this jolly cloth, cotton cloth we used because that is metal conveyor. In the side angle also, the movement of the conveyor belt you can see. Yeah. Yes, you can see. This is the conveyor belt system. Total movement of the from top load to down load, it will take 2 hours time. So first drying of total entire surface drying, it will take 50% of the moisture we can remove in one rotation. Second loading, we will stop the conveyor belt after full load, and at least 1 hour we recirculate the hot air. Later again, we will remove the surface moisture. At least for drying of the onion, tomato, it is taking 7 hours time. Leafy product in first batch, first round means within 2 hours, full-fledged drying is taking place. I think this is the clear. I think this is the virtual lab visit. Okay, virtual lab visit of the system. I think you people are somewhat visualized. I already some onions, whatever the onion. This is the dryer cabin drying. Temperatures inside the dryer cabin we achieved according to our need. Based on the product, the inside temperatures we have to change. For onion, for the effective drying, we kept onion directly means after 3 days also it will not dry. We have to increase more surface area. Create the capillary action not 2 meters length, means 2 feet depth we can't create. Maybe in of depth only we can create the capillary action by the movement of the air, hot air on the surface. So for that only, onion slicing machine separately we purchased for drying of the onion. After drying this one, the cost economics also we shown. I think with this I'm stopping my sharing. I think you people are at least some knowledge gained. I'm feeling. Now I am giving the session to the coordinator.
Thank you, sir.
Yes. Murali. If you have any doubts, you can ask, or whenever you are coming to our area, maybe Nandyala, you can visit our plants.
So, dear participants, virtual visit of solar dehydration plant is over by Dr. V. Sivardi sir. Now the another session by Dr. S. Murli Mohan sir on the topic renewable energy technologies, fuel cells and flow batteries. So sir is working as assistant professor in chemical engineering at NIT Warangal. Now I request Dr. V. Sivardi sir to introduce the today's resource person.
Yes,
Thank
no
you,
doubt. I forget that one. Yes, Dr. Murali is active person. As personally, I know because we both did PhD at a time. Very much active person. I have not seen like this person in all activities, not only education and all activities is involving and successfully is executing the things. That is very important. Involving means every person will involve all the things, but successfully he will implement. He is a very good researcher, especially in batteries, where the storage is a main challenging task. Flow batteries came and membrane. In batteries, a major role playing area is membrane. His entire research on membrane. I think we'll extract more knowledge from the Dr. Murali. He has published more than 20 publications in reputed journals, and one R&D project is implementing DST sponsored R&D project. And he guided one PhD. More than this, he's an active person, and because of his I think his friendship or in that tenure only, I learned more. Whatever I'm presenting in front of you, that is somewhat the motivation taking from our Murli only. But he's in NIT, I'm in RGM. That's all. That is only difference. I think with this introduction, I'm handing the session to Dr. Murli Mohan. Yes, Murli, yours.
Thank you, Siddhareddy sir. Thank you, Sivareddy, for a brief introduction about me. It is little more about me. Sivareddy is a good friend of me. At the time of we did, as he told, we did a PhD at IIT Delhi. We know each other personally. So coming to that, our program. So it is AICT sponsored 2-week faculty development program in renewable energy intervention industry, commercial and domestic applications. It is a very good initiative from the Rajiv Gandhi Memorial College of Energy and Technology in Nandyala. And I'll specially thanks and congratulate to the organizers, Dr. S. Siddhareddy sir and Dr. K. Tirupati Reddy sir. So thank you. I'll share my screen. So are you able to see my screen?
Yeah, sir. Okay.
So this is renewable energy, as FDP is focused on renewable energy technologies. So this is my research. I do research in fuel cells and flow batteries. So I'm connecting these fuel cells and flow batteries in renewable energy. How they connected actually? They think that many people think that renewable energies are solar and wind and tidal and these are all. But fuel cells and flow batteries are also the part of renewable energy. So as you can see, okay. So coming to my institute, it is NIT Warangal. This is a premium engineering college, one of the premium engineering colleges in NIT. So these are, we know that there are 31 NITs in India, 15 are old, 16 are newly established. NIT Warangal is very old. It is previously known as REC Warangal. Now it is from 2004 onwards, it is known as the NIT Warangal. It is considered one of the best among the NITs. And it is established in 1959. And recently, last year, we celebrated our 60th Diamond Jubilee year. And since 61 years, we are actually giving the technical education of our country. I am very proud to be one of the faculty here in Department of Chemical Engineering, NIT Warangal. And there are my research interests. I work in flow batteries and I work in direct methanol fuel cell. In this field only, I produced one PhD recently, direct methanol fuel cells. And I may ask Dr. Sivareddy, Professor Sivareddy mentioning, I make membranes for these fuel cells and flow batteries. And I also involved in wastewater treatment. So these are my ongoing funding projects. I am a principal investigator for this Spark project. It is a international project, international collaborative project with Newcastle University, UK. And I also co-instigator of one imprint project, which is industrial collaboration. We are working that name hybrid wastewater treatment systems with hydrodynamic cavitation biosurfactant for recycling of textile effluent. So this we are collaborated with the textile industry nearby NIT Warangal. So these are the two projects currently running, but because of COVID, these also affected a lot. So these are some of my selected publications. You can go to my Google Scholar also. You can see right now in which area I'm working and publishing my papers and writing the project proposals also. I would like to collaborate with you all people also if you are interested. I'm closely I daily talk with Professor Sivareddy also. So we also have thinking of doing some collaboration. So coming to our topic, see, this is the global energy demand. You could see these are the sectors where this electricity demand is there. We are using this transportation, residential and industrial, and how we are generating the electricity. At the bottom it is given. So we are generating the electricity from the natural oil and natural gas and coal. And this is the they are represented this with different color code. You can see oil green and natural gas red, and this is somewhat orange color, nuclear, biomass, and other renewable source, other renewable energies. So here in our country, the sector-wise residential energy consumption is given in the second figure. That is also you can see Asia Pacific, Middle East, Russia, Europe, Africa, and America, Northern America. So our usage is more, and generation is sometimes it is equal, sometimes it is more. When it is less, when it is more, then in between we have to bridge in between the generation and end uses. So mainly the major consumption is industrial sector. We are focusing here the usage. Conventionally, how we are generating the electricity, that you know as a mechanical engineers, most of you participants. So we are generating the electricity. How conventionally we are generating electricity from the steam turbines, right? So that also will be covered. So here we have to put our we have to replace the conventional electricity with that renewable energy. With that we can save much. But renewable energy, we know the solar energy, wind energy, and can you give me 1 minute? mark is there. I could not remove it. Coming on the screen actually. Sorry. Don't know where from this mark has come. Are you able to see this red mark right to this? I could not erase also.
Yes.
The big little bit. I'm stop sharing. I'll reshare my screen. Now it is better, right? That red mark, at least the big red mark is not there. Okay. So coming to the utilization of renewable energy, we know that solar energy, wind energy, wave energy, geothermal energy, and I include in this cycle electrochemical energy, the batteries and fuel cells. So how we utilize the renewable energy? We use this photovoltaic cells, solar cells, that effectively converts the solar energy directly to the electrical energy, and solar powered photochemical cells, production of hydrogen through water electrolysis. So hydrogen is one more renewable energy. So we use the hydrogen to generate the electricity through fuel cell. So in that way, and electrochemical energy conversion and storage coming into the picture in renewable energies. So photo electrochemical reduction of CO2 to value added chemicals. CO2 is more it is produced, and so if you can convert the CO2 to value added chemicals, that is also one good research area to, and it is also comes to provide the affordable clean energy. Okay, so in this way it is our electrochemical energy is linked with renewable energy. So we are talking in electrochemical energy also mainly electrochemical energy generation, that is fuel cell, and electrochemical energy storage, that is the flow battery. These two topics I am covering today's lecture. Okay. So if you see some reports, the International Energy Outlook in 2017, yes, Department of Energy, information experts, fossil fuels to provide the nearly 58% of the global electricity need, while renewables will collectively be responsible for the more than 31%. Okay, so what we are going towards, we are heading towards increasing the usage of renewable energy, means the energy generated from the renewable, and we want to reduce the uses of fossil fuels. Because why we want to reduce the uses of fossil fuels? One thing is they are depleting. Second thing is they are causing serious environment problems. So in fact, several news outlets have recently reported that solar and wind energy now as a turning point and cost nearly $50 per megawatt hour. Now stands nearly one of the price of the coal-fired power, but still the technologies should be improved and the cost should still come to should come low for the uses of for every residential uses. First, we will replace the renewable energies at an industrial level, then it comes to the domestic. Okay, then here how we can do that? These technologies, what is the energy generation and energy storage? Large scale energy storage technologies also bottleneck in respect to the rate. Their rapid development and deployment is critically important in order to realize the clean and sustainable energy in future. Okay. So This is the first slide in our fuel cells. See how the person is not a technical person, he is a marketing person. In 1960, he predicted that. He given this quote. It is a very famous quote. A score of non-utility of companies are well advanced toward developing a powerful chemical fuel cell. This is the quote about the fuel cell, which could sit some hidden closet for every home silently, kicking off electrical power. So we need not to put these grids and electrical wires and all. Just buy a fuel cell and that's enough. Put in one closet and cupboard. It will give you the electricity for your usage. That is what he predicted in 1960, and the technology is improving and it is heading towards this target is it is little expensive, means the electricity which is produced from the fuel cell is expensive. Our target, the research target is to bring down that cost. Okay, how we can bring down the cost? By using the cost, we can reduce the cost of the materials that we are using and improving the technology which we are using. By that we can bring down the cost. That's what research is going on in every segment of the fuel cell. Okay. So what is fuel cell? Why it is necessary? The fuel cell is a why necessity. I already told. Same the reason. The fossil fuels, they are limited in the amount of, the sooner or later they will be depleted, and their second reason is, I told, these are causing serious environmental problems, burning of the fuel cells. And so early in 1970s, the hydrogen energy system was proposed as a solution for these two interconnected global problems. Okay, so what is fuel cell? The fuel cell is a electrochemical energy converter that converts the chemical energy of the fuel directly into current, DC current. Okay, so you can see that in fuel cell there is a electrochemical energy generator. We are putting the hydrogen and oxygen and we are generating this. You can see this blowing of this bulb. In the external circuit, we are getting the electricity. These are the two outlets, that the waste heat and water, they will go out. These are the input, hydrogen and oxygen. The reaction I will show you. How we are, the working principle of fuel cell also I will explain. Okay. So this is the process, the conventional process of electricity generation from the fuels. How we are doing that? We are burning of the fuel. That means we are converting the chemical energy fuel into heat first. That heat is then used to boil the water and generate the steam, and that steam used to run the turbine, and from the turbine it converts thermal energy into mechanical energy. Then finally mechanical energy is used to generate run the generator which generates the electricity. Okay, this is the conventional process of generating the electricity. But with the fuel cell, we can avoid all these steps, and in single step we can produce electricity directly. Okay, so this simplicity which attracts this technology attracts the most of the researchers. So we are going towards that, and this is also renewable energy. Above all, this is renewable energy. Okay, first thing is how we are producing the electricity, that is conventionally from the fossil fuels, and this is from renewable energy. So the brief history, if you see, this is the William Robert Groove, but he is not a scientist, but he is a lawyer by profession, but turned into scientist. So anyone with the idea, they can give, they can be scientists, they can be researcher, they can invent many things. See here, his tenure is from 1811 to 1896. He invented the wedge battery in 1838. In 1800s, so this has discovered the process, the electrolysis process. Everybody is familiar with this electrolysis, right? When we give the current to the water, it produces the hydrogen and oxygen, right? You can see that some wires, when we put the wire into that to current the battery wires, if you put into the electricity like this, two rods, if you connect and put this, you can see the evolution of gas, hydrogen and oxygen, the small bubbles. So the thing is here, when we are giving the electricity to the water is forming hydrogen and oxygen. His mind worked in reverse way. When we combine this hydrogen and oxygen, can we produce this electricity or not? So combine these two elements and produce this electricity. So other way, we can produce the hydrogen from the renewable energy again. That's the other story. But when we combine these hydrogen and oxygen, can we produce the electricity or not? This is the starting point of fuel cell invention. Okay. So this is the Francis Thomson Bacon. He is a scientist from 1904 to 1992 and began researching alkali electrolyte fuel cell. There are many types of fuel cells are there. I will explain that all the types of fuel cells. He worked in this is the introduction part. So I am using just this is the history of the fuel cell. So he used alkali type of electrolyte in fuel cell in 1930s. In 1939, he built a cell that used nickel gauge electrodes and operated under pressure, high pressure. He operated, that is very risky. It is operated at 3000 psi. In 1958, he demonstrated alkali fuel cell using a stack of 10-inch diameter electrodes for Britain National Research Development Corporation. Okay, so you can see that in 1989, this is the big PC1401 by Perry Group. Is powered by the PEM fuel cell, and the car also it is shown in 1993. It is run by PEM fuel cell again. Again, I given the where from I taken these figures also. Okay, these are the application part where fuel cell researchers began and how they came into the application. Okay, so you can see that publication wise also up to 2008 I got the figure just to show that how in journals in scientific research journals how the researchers are publishing more papers and doing the research day and night in this area, fuel cell area. There are number of fuel cell related patents worldwide, but primarily from the Japan and United States. It's increasing dramatically nowadays. In India also it is not less. They are, you can search the papers in Science Direct or any other source. You can find number of papers from the Indians also in the area of the fuel cell. So it shows that how it is growing, the research is growing in the fuel cell area and the batteries also. Okay, so you can see this small stack of 10 cells, this one, and this is the bigger stack, and this is the 3 kilowatt stack, 48 volts. I taken from this figure from the fuel cell stores. How this fuel cell lives. You can see the more applications of fuel cell technology status and perspective. This is the title of this paper. You can see more information from this paper. So this is the 15 kilowatt alkali fuel cell powered tractor. Okay. This is one of the applications for the fuel cell. This is the fuel cell module. You can see the stack, and this is the megawatts by application: portable application, stationary, transport. These are the three sectors where the fuel cell application we can find. From 2009 to 2014, and this is the forecast is given megawatts by application. These are the 176 megawatts 2014, and it is increasing. And you can see this fuel cell park in Hwaseong City. It is South Korea. So you can see this clean. Any industry, if you go, this is not that much clean. But when you see the fuel cell, it is clean by itself. We are using hydrogen and oxygen only and producing the electricity. There is no moving parts, advantages I will explain you. How advantage of the fuel cell, what is the advantages and only disadvantages, few disadvantages are there. That are all, those are also being explained. Okay, so these are the advantages of the fuel cell. It is a very simple and directly it gives the energy. There are no moving parts, because of that it is very efficient. It is very quiet. When you see the turbines and generators, they are uh, you can hear huge noise, but these devices are very quiet. You can see that laptop or you can see your cell phone. They are not making any noise, right? So they are very quiet. So these electrochemical devices are quiet, and they deliver the energy also at the same time. They demonstrate high availability at lower temperature units. They can sit at any place. You can place this battery or fuel cell anywhere. They do their job. Okay, you need not to worry. So, and there is fuel flexibility also, and demonstrated the reliability of lower temperature units. Okay, for Indian conditions also it is very reliable. And what are the disadvantages? Because it is not mass produced, so there are not much industries registered toward the world. Because of that, they are extremely expensive. The components of the fuel cells are expensive. Of that, fuel cell energy, which is generated energy, that is also expensive. And no hydrogen infrastructure is provided. It means we need hydrogen, right, for running the fuel cell, but that hydrogen we have to give it. We have to generate the hydrogen first to run the fuel cell. So the infrastructure to generate the hydrogen also required to run the fuel cell. So that is not, if it is not supplied, then it is very difficult. It is expensive. Because of that, it is expensive again. That pure hydrogen is required again for efficient production of electricity from the fuel cell. We need pure hydrogen. If you have any contaminant, we expect that the device will be little less efficient. Okay. So some of the design features, I will tell the components of the fuel cell and how fuel cell is being designed. The heart of the fuel cell is, as I work in membranes, I will tell that it is the polymer electrode membrane which separates the two electrodes of cells. Actually divides the cell. Okay. If it is not, cell is short circuited, you cannot see any production of energy in the fuel cell. So membrane is out of the fuel cell. It divides on each side of the membrane. There are two porous electrodes. The electrodes must be porous because the reactant gas are fed from the back and must reach to the interface where the reaction takes place. Okay. On the catalyst also important. So a reaction actually takes place on the catalyst surface. That is also in the diagram I will explain. Technically, the catalyst layer may be part of the porous electrode or part of the membrane, depending on the manufacturing process, how we are making the membrane electrode assembly. So these three together, what is the three? Two electrodes and membrane is sandwiched between the two electrodes. That is called membrane electrode assembly. Okay. See this, whatever explained before slide, you can see the schematic here. This is the anode, this is the porous electrode, this is the porous electrode, this is the catalyst layer, this is the catalyst layer, and this is the membrane. So what is the role of membrane here? You can see the protons, H plus ions, travel towards, they are generated at anode and travels towards cathode, and from the external circuit, electron is going and coming to the cathode, and internal circuit is closed by these H plus ion transport from anode to cathode. So circuit is closed. Unless circuit is closed, you cannot experience any electricity produced in the external circuit also. Okay. If you remove this membrane out, then anode and cathode will merge together and you cannot experience any production of electricity here. So membrane electrode assembly consists of catalyst layer, gas diffusion layer, and proton exchange membrane. The whole unit is no thicker than a few hundred microns. I have shown you the little bit thicker to explain you, but it is not very much thicker. This is a micron size thick, and it has it can produce the power density up to 11 watt per centimeter square. Okay, and so further, this is MEA sandwich between the current collectors. Okay, the produced electricity, I will show it anyway. Little small video also is there. If you put these cells together, that is called stack, and it should have the outer cells should have some channels to flow to supply this hydrogen to the cell. Okay, and when you supply this hydrogen, that will go diffuse through this porous electrode and reach the interface between these polymer electrolyte and catalyst, and reaction happens at this point. And you will produce one electrode and proton. The proton will transfer to this cathode, and electron will transfer to the external circuit. You can put load here. Okay, you can capture the electricity there. You can see these different points. Oxygen is fed oxygen here, and these are the channels. This is the end plates which has the gas channels. This is the I'm not giving three-dimensional view. This is the one-dimensional. You can I will show you the video also. This gas is gone through the channels. These are the channels. Then it is diffused to the porous electrode and reach the interface, and the proton is conducted from the from anode to cathode. And here, whatever gas is produced, that is left from the anode collector. These all processes are explained here. All process, the electron produced here, that goes to the electron produced here, that goes to the external circuit. And 6th is water transport, 7th is also water transport, 8th is two-phase flow, unused gas carrying water droplets. 9th is heat transfer. These are the different processes at a time happening in the fuel cell. Okay, simultaneously. So when I show you the video, these all processes you can see what happens inside the fuel. Okay, these are the processes. I just I shown you the figure. Same thing. Gas flows to the channels first, and it reaches the porous channels. Then it flows through the gas diffusion layer. Then it goes to the interface of the catalyst and polymer electrolyte membrane. Then there is a reaction. Proton is produced. The proton is transported from the anode to cathode, and after that, proton is produced and electron is produced at the anode. The electron is gone to the external circuit. Proton is gone to the internal circuit. So proton is transported through the polymer electrolyte membrane. Electron is transported to the external circuit. Okay. Then at cathode, water is generated. I'll show you the chemical reaction. Then water transport also happens from the anode to cathode, and water is the outlet, byproduct, and heat and water. That is a schematic which is I shown in the earlier slide. So we are putting the hydrogen, oxygen, and we are generating the electricity, and that is what are the other products. We are producing water and heat. So how the fuel cell stack look like? This is the single cell. This is the black one. This is another black one. This is these two. If you say that these two are the electrode and end plates. So this is the bipolar plates they called. Okay, this is one bipolar plate. This is one bipolar plate, and this is the MEA. Okay, this MEA is sandwiched between two bipolar plates. This is called one single cell. Like that, you can see another single cell. If you put together all these single cells, this is called stack, fuel cell stack. Okay. What are the components in the fuel cell? You can see this is the membrane. We start from the membrane. This is the separating. This is dividing the cell into two different off cells, and this is the catalyst layers. This is the gas diffusion layer. These are the gaskets. These are the bipolar plates, which I'm telling. These bipolar plates will have these channels. Red thing you are showing, thing, right? Red. Those are the channels for gas flow. These are the either side. This will be connected to another cell. This will be connected to another cell. Interconnector. So like this single cell, if you connect all the single cell, that's called stack. Okay. You can see this video. Small video. Opening the fuel cell stack. This is the single cell opened up. You can see the flow channels, distributor, gas distributors, cathode, anode, and membrane. This is one single cell. You can see I explained as a schematic. Hydrogen and oxygen. Hydrogen is entered at anode side. Oxygen is entered at cathode side. Membrane is dividing both anode and cathode, and hydrogen we are pumping out, and at cathode side oxygen we pumped inside the fuel cell. Then reaction is happening at anode and cathode simultaneously, and the electron is produced at anode side, and H plus is transported from anode to cathode. See this, and hydrogen is mixed with oxygen and produced water and some heat. Okay. Same time, electrons is captured at external circuit. This is a small explanation also. Again, we don't need. So this is the working principle as I explained there. Same thing. Hydrogen gas is entered at anode side, and oxygen is entered at cathode side. So hydrogen is giving 2 protons and 2 electrons. 2 protons are transported through this polymer electrolyte membrane, and the electron is transported through this current collector here. See this? So here we are capturing our electricity. So the proton is reacted with oxygen and produce the water. If you clearly see this, you enlarge this section here, you can see this porous electrode. On this you have the carbon support. On that catalyst particles, nanoparticles are placed on which the reaction is happening. This is the interface of membrane electrolyte, polymer electrolyte and electrode interface. There only the reaction is happening here, and the electron is transported, gone there, because it is conductive material, a current collector. It goes on to that. From there we are connecting with the other electrode, so electron automatically passes through this circuit, and in between we can extract our electricity. Okay. So these are the few off-cell reactions. When H plus is transported through the membrane, then you can see these reactions. Overall reaction is H2 plus of O2 gives H2O, and also electrolyte, based on the electrolyte which we are using in the fuel cell. If you use the polymer electrolyte, these are the reactions. If you use this is called acidic electrolyte also. If you use base KOH, alkaline fuel cells, then OH is transported through the membrane, and there we have molten carbonate fuel cell. There O2 minus, CO3 2 minus is transported through the membrane, and in solid oxide fuel cells O2 minus is transported through membrane. Based on the electrolyte, fuel cell is divided into different types, classification. So here off-cell reactions, I will explain that. When you use the different fuel cells, these are the different fuel cell reactions, off-cell reactions. The overall reaction is same. Hydrogen is reacting with oxygen and producing H2. Okay, and when this reaction is happening, then we are also producing the electricity. Okay, why hydrogen is used? Highly reactive. When it is suitable catalysts are used, it can be produced from the hydrocarbons. So it can be produced from the water electrodes. It's also hydrogen. It has very high energy density. It can be stored for closed environment applications like space also. It can be carried easily. So these are the classification of the fuel cells based on the electrolyte which we use in the fuel cell. Fuel cells are classified as alkaline fuel cells. That is, in short, we can call it as AFC. And this is the proton exchange membrane fuel cell or polymer electrolyte membrane fuel cell. These can be used as you can use either of the names for these PEMFC. These are the most pioneered fuel cell in the fuel cell category. Okay, and direct methanol fuel cell, and there is a phosphoric acid fuel cell and molten carbonate fuel cell, solid oxide fuel cell. So you can see this classification, and as I told you in this PMFC, H plus is conducted from the anode to cathode, and in alkaline fuel cell, OH minus is transported from cathode to anode, and molten carbonate fuel cell also CO3 2 minus is transferred from cathode to anode, and in SOFC, solid oxide fuel cell, O2 minus is transferred from the cathode to anode. Okay, to see these cell reactions, when O2 minus, solid oxide fuel cell case, O2 minus is coming from the cathode, and it is reacted with the hydrogen at anode and producing hydrogen and 2 electrons. Then what this O2 minus, after producing the water, here also there are at cathode side, O2 is reacting with 4 electrons, okay, and producing this O2 minus. That O2 minus only reacting with hydrogen. First reaction is taking place at cathode, and second reaction is taking place at anode. Okay, O2 minus is reduced, reduction is taking place and giving O2, it is converting into O2 minus ion, and that O2 minus is transported from cathode to anode and reacting with the hydrogen and producing the water and electricity. Then OH, alkaline fuel cell case, then OH minus, again the reaction is simultaneously initiated at cathode first. OH minus is produced. That OH minus is traveled through the membrane and reacted with hydrogen and produced water and electricity. And when it is molten carbonate fuel cell, CO3 2 minus is produced at cathode. That CO3 2 minus is reacted with hydrogen and produced water and electricity. Either of the case, overall reaction, if you see, the hydrogen is reacting with oxygen and producing water and electricity. So the fuel cells also categorized based on the operating temperature. There are low temperature fuel cells and high temperature fuel cells. These are all called up to 120 degrees. These are all called low temperature fuel cells. These 600 to 1000 degrees MCFCs and SOFCs, they're called high temperature fuel cells. Okay, you can see that fuel cell types and applications. The operating temperature of the fuel cells, these are the column, operating temperature and charge carrier, already explained. Okay, the power range they produce, in what application they are suitable. The portable application, these low temperature fuel cells are suitable, and for distributed power generation and high, not domestic, not portable, the stationary applications, they are suitable. This is the solid oxide fuel cells and molten carbonate fuel cells. They need internal reforming of methanol reforming to produce the hydrogen. Any questions at this point? I had some voice, so I was asking. Not, I will continue.
From participant side, if you have any doubts regarding fuel cells, you can ask.
No, sir. No, sir, carry on.
Only you can carry on.
Anyway, I'll take at the end question and answer section. I'll take it at the end. Okay. Fine. Fine with the participants. Is it fine with participants? No problem for me to answer the questions at this point also. Not hear you clearly. Yes. You can put your question in chat box also. No problem. Chat box is also. Here I cannot see the chat box. I request Shivareddy to read the question if there is any question in chat box.
Till now there is no question, sir.
Okay. Then at the end we'll take the question and answer session.
Yes, yes.
Okay. Thank you. So these are the off-cell reactions. Little bit thermodynamics I will explain in the fuel cell chemistry. As you see that hydrogen is the anode side reaction is hydrogen is oxidized to 2 H plus ions are produced, 2 protons are produced and 2 electrons are produced, and cathode side oxygen reduced and combining with the 4 protons and producing this H2O. Net reaction is as hydrogen is combining with oxygen producing the H2O, and it is producing some heat. What is that heat? Heat of reaction means heat is associated with each of the molecule, right? When they are combined or when they are taken out, they will gain some heat or produce some heat. This is called heat of reaction. The enthalpy is associated with each of the chemical reaction. Okay, so there is a heats of formation of products or heats of formation of reactants. So enthalpy is associated with each of the components which are participating in the reaction. So products, enthalpy of the product minus enthalpy of the reactions, all heat of reaction. Okay, delta H. So delta H is calculated like this. H associated with the products, H associated with the reactants. H products minus H reactants. Here in fuel cell case, product is water and reactants are hydrogen and oxygen. If you see, the enthalpy is associated with the water is given at 25 degrees C is minus 286 kilojoule per mole, but it is 0 for elements. The elemental things will have the 0 enthalpy associated with that. When we combine, when the elements combine with some other molecule, then it will have the enthalpy. Okay, so as elements, they don't possess any enthalpy. So these hydrogen and oxygen are elemental. So because those will have the 0 enthalpy, and only here the product is water, and it has the enthalpy of minus 286 kilojoule per mole. Okay, so here heat is produced, that means it is exothermic reaction. Then it is taken to run the reaction, that is called endothermic reaction. Here then there is no net heat is loss or gain, that is called delta H is 0. We call that neutral reaction. Generally some heat will be absorbed or released when the reaction is taking place. Here it is a exothermic reaction producing 286 kilojoule per mole. Water is produced. If you say that 1 mole of water is produced by combining the hydrogen and oxygen. Okay, so the delta H is here and the delta G. Okay, delta G is Gibbs free energy. That is what useful energy. What is the useful energy? That exergy specialist, Professor Shivareddy. So he can tell that this is the T delta S which we are losing. This is the entropy associated with the system. So when we take out the entropy associated with the system from the enthalpy, that is nothing but your delta G. That is the useful energy. So you can calculate the efficiency also. output by input. Delta G by delta H gives the efficiency. So here you can see this HF, enthalpy of formation and entropy of the formation for each of the elements which are involved in the reaction. Hydrogen, oxygen, water, liquid, and water is in the liquid form and gaseous form. Here the values are given in this table. So using these equations, we can calculate the delta G and delta S of the this process. Okay, so when we calculate this, the heat produced in this system is 48.68 kilojoule per mole. Okay, remember this figure, 237 kilojoule per mole. This is we use the next calculation. Okay, so generally how we calculate the cell potential of the fuel cell. Okay, so hydrogen is giving 2 electrons, oxygen is reacting with these 4 electrons and giving H2O. This is the overall reaction. The electrical work is defined as Q into E. What is Q? Is a charge, coulombs per mole. Unit is coulombs per mole, and this is the specific work, electrical work, joule per mole. Because mole, why you are giving per mole? We are giving the chemical energy, right? So,
sir, sorry for the interruption.
Yes, yes.
Prasanna Kumar is asking something. I need some information about membrane shrinkage on the performance of proton exchange membrane fuel cell.
That actually, yes, Prasanna. Actually, the role of membrane we have discussed. The role shrinkage of membrane depends on the material which we are using for synthesis of the membrane. Okay, so when we are the membrane is not that much thermally stable, then because of that or because of chemicals that we are used in the fuel cell, because of that membrane will fail. Okay, membrane will shrink, or it may expand, or it may fall. It has a problems associated with the membrane. So whenever, see, when the membrane is healthy, then only it is efficient to produce the electricity. But when the membrane is diseased, like it got some disease like expansion or shrinkage or some problem, because of that definitely it will affect the your efficiency of the cell. That can be measured with the potentiostat galvanostat. Okay, how we test the fuel cell, that also I'll explain you. It is coming in the next slides. Okay, this is the what I'm explaining is the basic thermodynamics. What is the cell potential actually? We say that it is theoretical cell potential is 1.2 volts. What is that actually? So I'm explaining that. Hope your question is answered. Prasanna Kumar?
Yes, sir. Yes, sir.
Okay, thank you. So these are the electrical work is defined as Q into E. The Q is charge, E is the potential which is measured between the 2 electrodes. Okay, the Q, what is Q? Q again, the charge can be calculated with this formula, N into N average Avogadro number. This is the number of molecules per mole, and 2 electron, that means charge on 1 electron. Okay, charge on 1 electron is measured as 1.602 into 10 power 9 coulombs per electron, and per mole these many molecules are there. Okay, so this into this gives you the Faraday's constant. N average and Q electron will give you the total charge of 1 mole. Okay, total charge of the 1 mole per mole. So how many electrons are there here in fuel cell? We have two electrons. We will have the charge of 2 farads. Okay, Faraday constant is 96,485 coulombs per electron. but you will say that 96,500 is the Faraday number. This is the number which we use generally in electrochemical cells. So you see that work, electrical work which is done in the fuel cell, that is Q into E, that is nothing but NFE, and that is delta G. Delta G, I told, delta H is input, delta G is output. That is the electrical work we are equaling. There are no losses in the fuel cell, other losses, we are equating it to the electrical work, delta G. So if it delta G is equal to NFE, then what is the potential? E. E can be calculated. If you know the delta G, N in delta G by NF can is nothing but your cell potential. What is the cell potential in the hydrogen fuel cell? That is 1.23 volts. This is the theoretical voltage of the fuel cell. Okay, the maximum, the theoretically, when we calculated we taken into consideration enthalpies associated with each of the reactant and product. Then when we calculated like this, the maximum voltage which we can produce between these two electrodes is 1.23 volts per single cell. Okay, if you connect with the stack, we can produce more voltage. Okay, so but there are losses. If you see that, if you measure the voltage between these two electrodes, we can see that you cannot see 1.23 volt actually. This is called when there is no load connected, there are still losses in the fuel cell. What are the losses involved in the fuel cell? Is explained with this polarization curve. What is the polarization? This is the dictionary meaning I am giving. There is a division into two sharply abstracting groups or sets of opinions or beliefs. Means there are two sets like here current and voltage. We are taking current into voltage. So these are the two different sets. So with these two sets, we are explaining the performance of the fuel cell. Because of that, it is called polarization curve. It is one of the most common method for testing of the fuel cell. Okay. How it look like? I show the polarization curve, how it look like also. The polarization curve displays the voltage output of the fuel cell for given current density and loading. See, then fuel cell is there, it is generating some electricity, right? It is generating some electricity. That electricity is how much, what is the rate at which we are extracting that electricity? Means what is the current density we are taking out? Per centimeter square, how much we are taking out? Or per centimeter square, how much power we are taking out? That is the energy density or power density we are talking about. And the polarization curves usually obtained with the potential star galvanized. I told you already, this is the instrument which we measure this, which gives this polarization curve. Means already it has some resistances inside, so it is connected to the circuit. So with that we can draw these curves. We can get these curves from this instrument. So you have anybody can come here. Here I have one potentiostat galvanostat make of auto lab, that also can be seen, and fuel cell testing, how we do, battery testing, how we do, that also can be seen here. Okay, whenever you find time, whenever I may conduct this type of workshop or something, then definitely I will physically become, that is better. Offline it is very difficult to understand, as we have difficulty in understanding the industrial or any parts of this working, how it works and all. It's very difficult to get the point. When you have time, you are all welcome to visit NIT Warangal Department of Chemical Engineering. Okay. So, what are the voltage losses in the fuel cell? These are the losses in the fuel cell: kinetic losses and internal electrical resistance losses, and reactants, reaction sites, difficulty in getting the reactants to the reactant side, and there are internal currents, there are crossover losses. These are all explained here. Polarization loss. Yes. So these are the losses. This is the theoretical voltage which we calculated, 1.18 volts. Okay, but we are telling that voltage cannot be seen in the fuel cell because of these losses. There is a open circuit voltage loss because of that voltage loss caused by mixed potential and crossover. Crossover means one of the reactant is escaping from the one half cell to other half cell, which should not be. Means membrane has to restrict the passes of that particular ion, but it is not 100% ideal membrane. So some ions may escape from one half cell to another half cell. Because of that, these loss happens. Okay, and there is the activation polarization loss. You have to activate that. Minimum energy is required. Activation means minimum energy required to initiate the reaction, and the reactant has to come to the site, and reaction has to be initiated. Because before that, it takes some voltage, means energy. It takes some energy to start that reaction. That is the activation loss. Okay, so again, because of the components, you have the IR resistance. Lower means every component has its own resistance to flow the proton or electricity. So it is resistance is there each of the component. Electron has to flow from that reaction site to external circuit. That means it has to pass through every barrier. So each barrier has some resistance. So I into R, that is we are called ohmic losses. Ohm's law is V is equal to IR. So voltage is IR. So whatever loss because of that barrier is called IR losses or ohmic losses. So these are very less losses. The region of concentration polarization happens because of that ions are accumulating at the one phase at one place. So because of that, the clumsiness, the voltage drop happens. That is called concentration polarization losses. These losses are these combining all these losses called these are all total voltage loss happens in the fuel cell. Okay. Because of this, we cannot experience the actual voltage of the fuel cell. Okay. So these are the three distinct regions of the fuel cell in the polarization curve. There is activation polarization loss and ohmic loss and concentration polarization loss. So activation polarization loss are heavy. If you see this graph and compared to the ohmic and concentration losses are less. But when we go into the higher current densities region, then concentration polarization losses increases. Okay. So this is about fuel cell. Next segment is flow batteries, little bit. I'll explain you. Not that much detail, but already we spent of time, maybe 1 hour, I think so. Shall I give a break of 5 minutes, or shall I continue? It is not more slides. I will continue. I can continue. Yes,
you can continue, Murali. You may take 15 to 20 minutes, then leave to chat for doubts.
Okay, so question and answer session.
Yes.
Okay.
Prasanna Kumar is want to ask one more question.
Yes.
Yeah, Prasanna Kumar, please unmute yourself and ask.
Yes, sir. Yes, sir.
Yeah, please, sir.
So in hydrogen fuel, is there any hydrogen production in water electrolysis, sir?
So hydrogen is not produced in the fuel cell. Hydrogen produced outside of the fuel cell. It takes place in the methanol reforming in the refineries. You can see hydrogen production units. They are using renewable energies also for production of hydrogen. So whatever energy is required for hydrogen production, that is a different area. It is not included in the fuel cell. We are not touching that part, but hydrogen can be produced from the water electrolysis. Okay, that can be used. That renewable energy, the solar energy, can be used for the running of that water electrolysis. This is also means upcoming field. Water electrolysis using solar. Okay, so water electrolysis requires a lot of energy. If we can give that, if we can supply that energy from the solar, it is very, very attractive feature for producing the hydrogen and combining, means interconnecting the fuel cell with that hydrogen infrastructure. Okay, Prasanna Kumar.
Okay, sir. Then is there any optimization techniques for this processor?
Yes, there are optimization means there are, you want to talk about the process, then we have to enter into the process control, controlling the electrolyte flow rate and controlling the other things and simulations and all. There are studies for the optimization also, means we have to optimize the efficiency. One fuel cell law is there. I just maybe skipped if you, there are many parameters in the fuel cell. If you touch one parameter, it affects two other parameters. Okay, so optimization is required here. There are simulations or simulation. I'm an experimentalist, but simulations are going on this to optimize the fuel cell performance. Okay.
Okay, sir. Sir, can you give any influence points on this topic, sir?
Influence planes in that means
So concentration of electrolytic solutions.
here there is no concentration is hydrogen we are supplying, right? So hydrogen is pure hydrogen is required to get the maximum efficiency. Pure hydrogen and oxygen.
Okay, sir. Okay, sir. Thank you, sir. Thank you very much, sir.
Okay. Thank you, Prasanna Kumar. This is a
Thank
very interesting question. Good. You asked, you are participating. That is a good note to take.
Sir, it is nice, pleasant to associate with you, sir.
Thank you. Thank you very much. Can I continue further?
Sir, sure, sir.
Okay. Thank you. This is the electrochemical energy generation. Now, how these flow batteries also connected with the renewable energies. So flow batteries also, it is not generation, it is purely storage. Why electrochemical storage is required in renewable energy? As I explained, there is a solar energy. Suppose we are producing, there is a PV cells are there, we are producing the electricity and we are getting the electricity, right? Directly we connect it to the usage endpoint. Sometimes solar energy is produced, sometimes at night. What is the situation? We cannot get any solar energy. That means there is no power at end usage. Means if I am a resident, domestic usage, I have installed some solar power panels at my rooftop, and if daytime I am directly getting the current generation, so my appliances all are running. But what about night time? So I want to say that these renewable sources are intermittent. That means they are not continuous. Sometimes they will be there, sometimes they may not be there. That means even in the daytime also, if it is a cloudy day, then we cannot get the solar energy at the same point. Okay, so in between the barrier, the bridge is required to we have to put a bridge between the solar energy, then means renewable sources of generation to the end users. What is the bridge? Bridge is nothing but our battery storage. So for stationary applications, if you can put, whenever it is more it produced, we can store that energy. Whenever it is required, we can use. It is like a bank, saving bank. We are earning and somewhere we are storing, right? We are saving account we are calling. So whenever it is required, we are withdrawing. Same type, whenever it is required, we can take it from the battery. The battery acts as a bridge between these generation and end usage. This is the traditional generation or renewable energy generation. Whatever it is, the excess generation or excess demand, the bridge is electrical energy storage. Okay. So from here we can divert the energy to the end users. Okay. So why the flow batteries? This is the stationary applications. Flow batteries are very high capacity, high power, and it has a long cycle life. Okay. And you can compare these lead acid batteries. These are the liquid type batteries, and this is the solid type batteries, lithium ion batteries. This all comparison I given. At this point, I am focusing more on flow batteries. the discussion is not that much important here, but you can see this flow battery, how it is advantageous. Traditional battery, lead acid battery, is a single unit. All electrolyte is inside, anolyte and catholyte, and the reaction is taking place. Whatever the reaction taking place, and the energy is stored in the inside only. Okay, but when coming to the flow battery here, coming to the flow battery, the electrolyte is stored in external tanks. Then it is pumped. Only reaction is taking place inside the cell. There is no storage of your electrolyte, charged electrolyte or discharged electrolyte. In this way, we are partially decoupling the energy storage and power. Okay. So in this way, we can increase the efficiency of the flow battery. So there are different flow batteries. These are all batteries, different storage, electrical storages, zinc, air, lead acid, nickel, cadmium, lithium ion, sodium sulfide batteries, flow batteries. So flow batteries are in between when we compare capital cost, the y-axis capital cost per cycle. So I worked in this vanadium redox flow battery for my PhD. This is the anode side reaction. This is the cathode side reaction. This is the overall reaction. So this is why vanadium can exist in 4 different oxidation states. At anode, it can exist in 3, 4, 2, 3, 4, 5. These are the 4 oxidation states. Because of that, we can eliminate the cross contamination between the anolyte and catholyte. Okay, because of that, it has more advantages than other type of battery. Okay, so most I focused, there are different areas to work in flow battery also. There is electrolyte part, electrode part, and membrane part. So electrolytes also, they are worked about this vanadium ion solubility in H2SO4. And electrodes, there are different electrodes are there to minimize this gas evolution and all, to increase the efficiency. But I choose the membrane stability and selectivity, conductivity of ion. Okay, so I worked in this area and I successfully developed 3 different membranes. You can see those publications online also. Okay, from my PhD, and one more publication after graduation, after taking the degree, I meant to write that paper actually. Okay, so these are the different types of flow batteries, and these are the advantages and disadvantages associated with each type of flow battery. But most prominent and most advanced technology flow battery is vanadium redox flow battery right now. Commercially, we can see some installations also. At the end of the slide, I will show the installation, how much power we are producing, how much power we are storing and giving back this flow battery chemistry. Okay, and there are excellent review articles of the flow batteries. These are some of the review articles which you can see in the online. You can just type online flow batteries. You can use, literature is available. These are the review papers, review papers which gives the insights into the flow battery. Okay, so if you come to the history, it is started in 19th century. It is 21st century. It is actually development has taken place in 20th century, and we are moving to the 21st century. So first flow battery was invented by the French scientist named Charles Renard in 1884. Okay, but that his invention is forgotten for many years, and after that it is revived by this German scientist called Walter Kango in 1954. This means it is 20th century, it is revived again. It is invented in 19th century, but reinvented in 20th century. Okay, so after that, NASA has taken this project. NASA flow battery is undertaken by the NASA in 1970, and there are many advancements after that. I will give you the goals, year goals of this NASA, how it is explored the flow battery chemistry. Redox bubbles, they screened iron, chromium, vanadium, ferrous oxide, chromium. These are the redox couples they screened, they put into that battery for storing the energy and discharging the energy. And after that, they have tried different electrodes. And NASA, they effort, finally they have given this chromium is good, attractive. It is the less expensive and giving the good efficiency also. And when we screen the electrodes, they have screened the different electrodes like cloth, felt, carbon felt, foam type, chips. They are all their electrode types. They explode. Okay. The electrodes also, the different types of electrodes also they explode. Okay, these are the milestones they are given by the NASA. Later work 1980 and 82. The cell stacks and the integration with the solar cells they made. They integrated the solar cells, vanadium not vanadium, redox flow battery. So they are, and the cost prediction, their optimization, the pumping losses, shunt current, and they work with the mixed reactants, and they work with the elevated temperatures to improve the efficiency. These are all studies are taken place in the NASA. Okay, so how it looks like? It looks like same. The components which I have explained already in the fuel cell, it looks like same with the same component it works, but whatever putting inside the feed is different, the reactions are different in this. Okay, except that everything is same. What are the differences? Little bit that I will explain. I'll compare the fuel cell and flow battery also. As I told, this 1954, the German scientist, he is patented. So invented is 1854, but 1838, but that person is not patented. The patented technology has come now. We have to patent immediately. Okay, so because he is patented, because of that only we could know this on his name, Walter Kango, storing this electrical energy in the liquids. Base material is titanium chlorine. He worked on this and hydrochloric acid, the electrolyte. So the NASA is picked up the ball. 19 years further, 1973. Okay, they produce first iron and chromium redox flow battery and store the energy for the future moon base. So NASA is always, it is from my childhood also, you would also heard of this. They want to go to the moon. So for this purpose, they want to store this electrical energy in the liquid form. So they explore the redox flow chemistry, redox flow batteries. But the moon base never happened because the target is shifted to the Mars. But this also may happen or may not happen. I don't know how far it is true going to the other planet. Okay, with this body. But we believe that NASA is still in hope of going to the other planets. Okay, so anyway, they have invented, they have taken this challenge that and the research is advanced further because of NASA. They started with the iron and chromium, but they screened different redox flow couples, as I explained in the previous slide. Okay, and the commercial research continued to uranium and zinc bromine flow batteries, but these are too hazardous. 1984 is the turning point, you can say. Then University of New South Wales in Australia, they built vanadium redox flow battery. This is the first time there is a same chemical on either side of the flow battery on the membrane. So we are hoping that this hold key the redox flow battery chemistry, replacing the coal and nuclear power stations with wind and sunshine. Okay. Since then, vanadium is in the spotlight. Okay, this technology in the spotlight, and the research is more focused in the vanadium redox flow battery, developing these electrolyte membranes and electrodes. So as I told, I worked in this area for this redox flow battery. Okay, for my PhD. Now I am working in fuel cells and flow battery, both the areas I am working. I am working on electrodes also, I am working on electrolytes also. I am not working on flow fields designs. This is completely theory. more simulation work, more type of simulation work. CFD simulations are going on this IIT Madras, some IIT Delhi. They are like Professor Srinivas Jayanti, Professor La, Professor Dorma, Professor Basu. These are all working, and simulations also. There more information is available. There people are working in different areas. So this is a comparison with the fuel cells and flow batteries. Reactants are gas, here liquids, means active material is dissolved in. Is expensive, catalysts are used here, but here that is not required. Electrode design is thin MEA. Here it is flow area, that's all. So is the flow area is required, not that much infrastructure is required. Membrane is cation exchange membrane. Here cation, anion or microporous membrane also can be explored in this. Bipolar plates are same, and cell structure is plate and frame. Here also same. That's all. Here extra infrastructure is hydrogen storage is required. Here extra is tanks, outside tanks are required. Okay, for storing the electrolytes. This is the redox flow battery. There is a storage tank for storing the electrolyte. Anode side electrolyte is called anolyte, and cathode side electrolyte is catholyte. So they are pumped into the cell. The off-cell reactions take place, and the active material is converted into other oxidation state and store the energy. When the reverse reaction happens, then the stored energy will be generated back. So this is the chemistry. This is the anode, this is the cathode. This is having different oxidation states. 2+ is charged, 2+ is reduced to 1+, and cathode side 2+ is oxidized to 3+, and discharge size reverse reaction happens, and your electricity is that. The charge discharge cycle basically. So this is how your flow battery looks like. The flow battery also we can call it as a regenerative fuel cells, because it is a one time it is charging, one time it is taking electricity, and the other time it is giving the electricity back. The components more or less it is like fuel cell only. Okay. Only the chemistry, reaction chemistry inside that is different. So the flow battery is an electrochemical device that converts the chemical energy into electroactive materials directly to the electrical energy. Yes. So this redox flow battery comprised of two parts that are connected through the pumps. The flow cells consist of two parallel electrodes separated by this ion exchange membrane, as I told you, forming two electrolyte chambers. One is the anolyte chamber and the electrolyte chamber. This is the two off cells. The separate electrolyte solution containing electroactive material circulates through each of the compartments from the independent electrolyte circuit. The two circuits are running here, unlike the fuel cell. One is anode side circuit and another is cathode side circuit. Two different reactions are taking place at anode side and cathode side. So electroactive material is very important. That dissolution of electroactive material inside the electrolyte, that is we may use acid or some other electrolyte. We have to dissolve that electroactive material which is really participating in the reaction. Okay, so the total energy stored is governed by this electrolyte concentration and volume of the tank. Rather, it's being constrained by the electrode, because other lead acid batteries, it is totally everything is inside. Here we are separated, that storage and everything. Only reaction is taking place inside the cell. The storage is taking place outside the cell. So the energy stored is governed by that electrolyte concentration. How much electrolyte concentration means the electroactive material is dissolved in the liquid aqueous material. Sometimes it is acid, sometimes it is a base. Okay, that should be ionically conductive material. And volume of the tank size. With this, we can determine how much energy is stored in this flow battery. And power rating, mainly power rating is depends on the cell. Okay, how much area is there, electrode area is available, and what the reaction is taking place. When the reaction is taking place, then only the electrons are released. Based on that, only power rating is dependent. Okay. So these all explained. Only thing is that different types of flow batteries are there. That is also I explained different types of flow batteries. So active material in the electrolyte, that based on the electrolyte that we use in the flow battery, that determines the type of flow battery. Okay. This is all explained in negative electrode. What is the reaction takes place, and cathode, what is the reaction taking place. So as in the fuel cell, the electron is passed to the external circuit, the ion is passed to the internal circuit to close the circuit. Otherwise, the charge and discharge won't happen in the flow battery also. So one single example, if we can take, I'll explain all these points in the figure. See this vanadium redox flow battery. What is happening? This is the charge cycle. Focus on this charge cycle only. When we are putting the charge, means when we are pumping the electricity inside the battery. Okay, this is the E4 is oxidized. Okay, E4 is oxidized. Before that, when we are pumping the electricity, electron is pumped inside, right? The electron is taken to this, and V2, V3 is reduced to V2. Okay, reduction is taken place. V3 is reduced to V2, and here oxidation takes place. V4 is oxidized to V5. Okay, in this form, when we are charging, the ions are the active material is in one half cell it is oxidized, in another half cell it is reduced. Okay, this is the active materials all are now converted into different oxidation types, different state of oxidation type. Okay, when discharge happens, these reactions will be reversed. See this, when the discharge happens, electron is taken here, right? Now electron will be produced here. Okay, when we are charging, the source is connected. When we are discharging, the load is connected. Okay, fuel cell case, that is very easy, only electricity generation. Here it is storing and giving back. Means generation is not happening, it is storing and giving back. Storage, electricity storage, and reverse reaction, we are getting back the whatever stored. So 3-element stack, you can see. This is also, we can make it as a stack based on the power output which we need. So this is how it looks like. So as I told you, different types of flow batteries based on the redox couple which we use in the flow battery. This is the iron chromium flow battery. This is the reaction happens. This is the potential of this, theoretical potential of this flow, iron chromium flow battery. Okay, and there is a all vanadium flow battery. It is also around 1.24 volts. And this is, so these two are combined here, hybrid battery they made, vanadium and ferrous, gives the 1.2 volts. It has its own advantage. This is called hybrid battery. They made this hybrid battery with combining the two different batteries. Vanadium flow battery, from all vanadium flow battery, they have taken one redox couple, and iron chromium battery, they have taken another redox couple, and they combined, they have made different hybrid battery, hybrid flow battery. Okay, so there is a research is going on. The active material, based on the active material, the cost of the battery is increasing. So they want to decrease the cost Department of Energy US also set the targets. Based on that, the research is going on to reduce the cost of the flow battery and mainly the cost of the electrolyte. So they want to shift that research area into that phenol based flow battery chemistry. They want to use this anthraquinone based membrane based electrolytes. These are the organic, they are called organic flow batteries. You can explore more about organic flow battery. Such you can have more insights into the phenol based flow battery. Okay. So how we test this flow battery? So this is the efficiency which we can calculate. There is a constant current mode. There is a means how we are extracting the power. Constant current, we are constant power mode, constant voltage mode. When we connect this flow battery to the potentiostat cardinalstat, we can do these testings. Constant current mode testing, constant power mode, constant voltage. These are the curves looks like. When we test the battery connected, only we are maintaining this current. Constantly we are extracting this current. Charging, we are giving this charging, when we are constant current we are giving in charging and constant current we are taking out in discharging. Then you can see the other two curves, voltage and power, how they are varying. Similarly, constant power, similarly there is a constant voltage also. Finally, the performance is calculated in charge cycle, how much average voltage is maintained, and discharge cycle, how much average is maintained. V discharge by V charge is called voltage efficiency. Same way, we can get the how much charge is maintained in this while charging, how much charge is maintained in discharging, that is Q charge by Q discharge. Then when we have this is called Coulombic efficiency, and Coulombic efficiency into voltage efficiency is nothing but energy efficiency. When we have this, when we talk about the flow batteries, mainly how much energy efficiency is maintained in the flow battery, that is very important parameter. So how this parameter comes into the picture, when we multiply with this Coulombic efficiency with the voltage efficiency, we can get this energy efficiency. So this is the power which we are getting back using these flow batteries. 39,664 kilowatt power we are getting back. So 113 vanadium redox flow battery installations globally, you can see, including India. India have 4 installations. So commercially it is growing up. So you can see this solid batteries are graph is coming down, cycle and charge capacity has high charge capacity because of that. For stationary applications for renewable energies, this flow battery chemistry is preferred than other battery chemistry. So the research is going on. This already explained the electrolyte cost want to reduce. So with this, I conclude this presentation. Thank you very much for your attention and listening. So if you have any questions, quick questions I can take, please.
Yes. Now session is open for discussion. So expert with us.
Sir,
Yes, please.
sir, a small question from previously you told about the
Yes, Prasanna Kumar.
sir. Previously you told about the thermodynamics in fuel cells.
Yes, yes.
So on that basis, how the enthalpy formation on material?
See, enthalpy is associated with each of the molecule component, right? Means compound. Molecules combining together forms the compound. So when they are forming the compound, it is a formation, enthalpy of the formation. It is a constant data is available, the tables are available. That means experimentally they found out enthalpy, the energy associated with the compound.
Sir, sir, how it is vary on hydrogen cells and that flow batteries?
See, flow battery, it is a fuel cell completely about the generation part, right? We are only generating. Here, it is not generation, it is a charge discharge. Okay. Here also thermodynamics are involved. It is mainly we are giving the current. We are giving the current into the cell. We are taking back the current. So the efficiency is calculated based on the charge and discharge. But there is efficiency is calculated based on the input and output. Okay. Here we'll measure the average voltage maintained in the discharge cycle, average voltage maintained in the charge cycle. Here we are not measuring like that. So the evaluation techniques means how we evaluate the performance parameters in the fuel cell is different, flow battery is different. So the energy associated here, no formation is taking place. There is a formation. H2 is formed. H2O is formed. H2 and the O2 is combined, and H2O is formed, and we produce some electricity. Because of that, that voltage is produced. Here it is not like that. Clear, Prasanna?
Sir, clear, sir. Thank you very much, sir.
Okay, thank you.
Very informative session, sir.
Thank you very much. Any other questions?
Please unmute yourself and ask questions. Not questions, you can share your experiences. For any research proposal, you want any inputs required also, you'll support.
Professor Sivaradi is available there. He has direct contact. For collaboration, I don't have any hesitation. Already he is a collaborator. Sivaradi sir is also available there. And my contact details also shared, right, in the website, in your browser.
Yes.
So,
Dr. Murali, NIT Warangal, you can type, you will get everything.
Yes, yes.
In chat box, one feedback is there. Thank you, sir. Excellent session, sir.
Thank you very much.
I think now we will end the session. Thank you, Murali, for your valuable inputs. And we are expecting that related second project also. If time permits, we will take you.
Yes, definitely.
Regarding wastewater treatment.
Definitely, Professor Sivaradi. Definitely.
I think for the participants, afternoon 2 o'clock, the resource person is Dr. NL Panwar. I will introduce him because he is one of the pioneer scientists in renewable energy. Out of 2% researchers available in renewable energy, he is one of the scientists available in India. Especially Maharana Pratap Agriculture University is doing a real R&D for rural sustainability. I think we can extract more experience from Dr. NL Panwar. So session will start sharp 2 o'clock. I think now we are hand over to the coordinator if you want to give any inputs.
Okay, thank you, sir, Murali sir, for accepting our invitation.
Thank you, sir. I started my presentation thanking you and your institute for conducting such a nice FDP. Thank you.
Sir, I sent an email to you. You please respond, sir.
Yes, sir. Definitely.
Yeah. So thank you, sir, once again. So we'll close it.
Yes, sir. Thank you.
You can leave, sir.
Can I hang up, sir? Can I leave the meeting now?
Yeah, leave, sir.
Okay. Thank you.